Good morning and welcome to the ASV's coverage of NACAA 2022, the National Australian Conference of Amateur Astronomy. Today we hope to bring you some very interesting talks on all areas of amateur astronomy. But before we begin, I would like to say that in the spirit of reconciliation, the Astronomical Society of Victoria both acknowledges the traditional custodians of country throughout Australia and their connections to land, sea and community. We pay our respect to their elders past and present and extend that respect to all Aboriginal and Torres Strait Islanders today. Remember, if you have any questions, pop them in the chat and we'll get to them at the end of the stream. And if you're enjoying the stream on Facebook, you can donate stars. On YouTube, you can donate stickers. They all go towards the ASV's STEM observatory, our remote observatories we're trying to build. And if you're watching it for the first time, don't forget to subscribe to both ASV and NACAA on YouTube and ASV and NACAA on Facebook. Today's first presentation will be presented by Dr. Russell Cockman. Russell is the ASV's current solar section director. He is a retired industrial chemist who continues to share his passion for science by lecturing chemistry at RMIT University in Melbourne and has an observatory guide at Melbourne Observatory. Russell's presentation will cover the highlights of Solar Cycle 25 and will examine the various features of the sun worth viewing, as well as focusing on highlights of Cycle 25 so far and what will be expected over the next few years. Russell, welcome.
Thank you very much, Mark. Hello and a warm welcome for joining this NACAA presentation of the highlights of Solar Cycle 25.
I'll let you get right into it.
Okay, well, thank you very much, Mark. Just keen to get going. So this is a presentation prepared by John Wilkinson, an avid solar photographer and member of the Astronomical Society of Victoria. But unfortunately, John is unable to give the talk today, so I'll be presenting it in his stead. So John, if you're listening in, I hope that I do justice to your excellent work. Firstly, we're going to look at a few aspects of the activity on the sun, and the activity on the sun is monitored by recording and observing a number of features, and these features are sunspots, those dark spots that we see on the sun change from time to time, a feature called flares, and prominences, and coronal mass ejections. And there'll be examples of each of these effects as we go through the talk, so you'll know exactly what we mean by these terms. And these features vary with an approximately 11-year cycle. And we now know that this cycle is due to changes in the sun's magnetic characteristics. The sun is a huge ball of plasma, that is charged particles, and when charged particles move, as they do so inside the sun, that creates magnetic fields, and the magnetic fields of the sun create all of these features that we see above. Now here's a lovely image taken by John on the 26th of November 2020, showing what we would say is the sun in white light, so that lets all wavelengths through, except John, as we will see, uses a green filter for his imaging. But here we can see a lovely large sunspot there, and sunspots are given numbers. So this large sunspot is known as AR, which stands for Active Region 2786, and that little spot below it, well, little compared with that big one, is AR 2785. Now, although we don't see the entire sun in this field of view, if you can imagine that we can fit 109 Earths across the diameter of the sun. So although those sunspots look relatively small compared with the size of the sun, they are huge compared to the size of the Earth. And there's a description of what sunspots are. They're temporary dark spots on the photosphere of the sun caused by intense magnetic activity, which inhibits convection, that is the rising up of heat and the falling down of heat within the sun itself. This in turn produces a lower temperature region, so they appear dark. And that lower temperature is probably only a couple of 100 degrees Celsius lower than the average temperature in the vicinity. So that difference in temperature is enough to create a sense of darkness against the lightness of the surrounding area. Now this is the monthly sunspot cycles 23 to 25. Every sunspot cycle is given a number, And currently, as the title of this talk indicates, we are entering cycle 25. That's C25 here. If I bring my cursor up. So there's C23, which took place between about 1996 and 2009, and then the last cycle, cycle 24. And you can see that from one cycle to the next, the intensity of the cycles are different. And so this is the interesting aspect of cycle 25. How active is it going to be? Cycle 25 began in December 2019. That was when the cycles start at solar minimum and then carry forward. So that was solar minimum. And cycle 1 began in 1755, all those many, many years ago. Now here's a slightly different representation of cycle 24 and cycle 25. These are daily sunspot numbers. You can see along the vertical axis there, sunspot number and dates all the way from 2010 to currently, over 12 years or so of data. And one of the highlights so far of cycle 25 is that at the present time, here we are, the sunspot number is larger than it has been since about towards the end of 2015. So that's 7 years ago. So we are seeing the solar activity at its highest level in over 7 years. That is certainly a highlight so far of cycle 25. Now, flares are sudden and violent releases of energy and matter within an active region. So those regions which are labeled AR number, such as AR 2838, and these are classified as A, B, C, M, and X on increasing energy. And so this is a logarithmic scale. So X-class flares are 10 times more powerful than M-class flares. M-class flares are more 10 times more powerful than C-class flares, and so on. So an X-class flare, the most powerful flare there is 100,000 times, roughly, as energetic as an A-class flare. And here's an image of that John took of an X-class flare, actually X1.5, on the 3rd of July 2021. That's that white spot here. So the energy released during that flare heats up the surrounding air and causes it to be hotter, and hence glows a lighter red than surrounding. And this is an image in hydrogen alpha, and look at all that beautiful structure we'll see as we go along. These are all structures in the sun's chromosphere, which is the layer of the sun that we see when we view the sun in hydrogen alpha. And we'll cover what these other features are as we go along. So that's how we see a flare, is a lighter patch against the slightly darker solar background. Here's an image taken on the 15th of August 2021, and on the northeastern limb of the sun, it shows a prominence. Now, often people, when they see these features, they call them flares. Well, it's the flares that actually create these features, or largely, but these are called prominences because they are prominent off the edge of the solar disk. So these are prominences. And once again, comparing the size of the Earth, I reckon the Earth would sort of be about this size. If you can see my cursor going around and around, it'd be about the relative size of the Earth compared with this prominence. They are huge. And in general, a prominence is a flame-like structure seen around the limb of the sun in the light of hydrogen alpha. Before we go on, let's have a look at the sun's spectrum. As we know, the sun emits visible light. There we are. We see it. That's what lights up the landscape for us. And this is the spectrum of the sun, all the way from violet to the deep red. And when we go to shorter wavelengths, we get into the ultraviolet region, and shorter wavelengths still into gamma rays and X-rays. And these are all radiations that the sun produces. Naturally, much of these are eliminated from our reaching the ground by the Earth's atmosphere. When we go to longer wavelengths now, going from towards the red end, We get beyond the visible region, we get into the infrared, that's heat, and longer wavelengths still, we get microwaves and radio waves. And it is truly incredible that every aspect of astronomy and solar astronomy covers that entire wavelength of electromagnetic radiation that we see here. Now, John uses two wavelengths to observe the sun, and he uses a white light telescope, but with a green filter at 540 nanometers to improve the contrast, and also observes in the light of hydrogen alpha, which is deep in the red at 656 nanometers, and that's the hydrogen alpha absorption line here in the solar spectrum. Here's a lovely image of the southern hemisphere of the sun taken on the 28th of August 2021 in 540 nanometers. So that's effectively a white light image which shows up sunspots beautifully. So here's a relatively small sunspot group, AR2860, containing several large spots and lots of smaller ones, and there's 2862 on the very edge of the sun. Now here's the same view of the sun, but taken in hydrogen alpha on the same day, and no doubt you can see the difference. That active group has got some flaring activity associated with it. We can see prominences around the edge of the sun, and we've got this feature which is labeled F on this diagram. So what does F mean? So F is called a filament, so it's a prominence seen against the solar disk. And because filaments are slightly cooler than the solar disk, they appear slightly darker in comparison. And that flaring we see here from AR2860 was an M4.7 flare, a relatively intense flare on the 28th of August 2021. So hopefully you're seeing that whatever wavelength we view the sun in, we get different views of the sun, and hydrogen alpha is a marvelous way to view the sun. 6th of September last year at 540 nanometers, there's a sun festooned with sunspots, AR2866, etc., large and small, dotted across the solar disk. And this is what we expect to see as cycle 25 boosts in intensity, more and more sunspots on the visible sun. And this was taken 3 days later. I'll just page up. There we are. So just keep an eye on 2866 here, just memorize how it looks, and I'll look at the next one. You'll see how 2866 has grown, but also it's moved in position. 2866 was over here 3 days ago, and now it's there. This shows us that the sun actually rotates, and the rotation period of the sun at the equator is around about 27 days and about 35 days at the poles. And it was back in the 1850s when solar astronomers observed sunspots, they noticed that they moved across the solar disk, and that proved that the sun actually rotates, and that the sun actually, the rotation speeds of the sun differ in latitude, and therefore the sun cannot be a solid object, but a big ball of gas. Can learn a lot from sunspots. Okay, so sunspots are a visible measure of solar activity. This is something that we can do from space. We can measure the intensities of flares and count the number of C, M, and X class flares per month. And as you can see, this is 30th of August to the 27th of September last year. And we've got the lowest energy flares. C class flares are the sort of the brownie color, M class flares in red, and the most energetic flares of all X class flares are in this magenta kind of color. So really, over this month, not a lot happened. Lots of C class flares and one M class flare here. And please just note the vertical axis here from 0 to 8 number of flares per day. Keep that in mind, please. Here's a beautiful image of the sun in hydrogen alpha, showing the full disk with lots and lots of features, prominences around the edge, filaments on the disk, lots of active regions, some active regions flaring as we look at them. Most magnificent view, and this is a typical view in hydrogen alpha that the eye would see through a hydrogen alpha telescope, except that the sun is more beautifully radiant red than what we see here. That was on the 23rd of September. 26th of October, about 10:30 a.m., there was an eruptive prominence on the edge of the sun. So here it is, the beginning of it. So a flare had exploded, sending solar stuff into space. So that, remember, this is 0030 hours UT. And here's an image taken just 10 minutes later. Notice how the prominence here has changed its structure. This is in 10 minutes, ladies and gentlemen. 6 minutes after that, change its structure again. And then 12 minutes later, the prominence is just about gone. So that's an eruptive prominence seen almost with your own eyes, the dynamics of the sun, almost with your own eyes. Fabulous series of images. On the 27th of November 2021, the southern hemisphere of the sun was a delight to observe. Some small prominences around the edge, an active region 2898 flaring and 2900 flaring, some large filaments, and all this granulation on the solar chromosphere is real structure, not just imaginary structure. And you can see that with your own eye in a hydrogen alpha solar telescope. On the 18th of December 2021, in the southern hemisphere, looking on towards the eastern edge, you can see lots and lots of sunspots, lots of active regions. An active region up here, 2911, emitted or exploded a class M 1.2 flare on December 17th. Ten days later, or thereabouts, a very, very different view of the sun. Large sunspots and complex sunspots have appeared, lots of them, in white light. And hopefully you're realizing that as we go forward in time, we are seeing larger and more complex sunspot groups, an indication of an uptick in solar activity, as we would hope to see in cycle 25. Here's an image of the sun on the 30th of December 2021 in hydrogen alpha, prominences around the edge, active region here 2916, 2918 up here, and have a look around the active region here. Now remember, these active regions are created by magnetic lines of force, and you can see that around the active regions we're actually starting to see those magnetic lines of force cause the plasma to follow certain directions. Bit of order there compared with the relative randomness of the structures around it. Beautiful to see in hydrogen alpha. And here's exactly the same sun taken on the same day, but in white light. Sunspots are more visible, but no prominences, no chromospheric granulation, and a very, very different appearance between the two different wavelengths. Righto, we're coming up into this year now in hydrogen alpha, this wonderfully active sunspot group AR2924, active regions, and here you can see the structures around these active regions caused by magnetic lines of force. A wonderful image. January 29th, two images taken on the same day of the same region of the sun, AR2936 on in white light here, and compare the difference in hydrogen alpha. Sunspots are far less apparent in hydrogen alpha, but to make up for that, we can see flaring activity, etc., etc. So one observation complements the other. As you can see from the description here, this is an M1.1 flare from AR2936. Now these flares may only take 10 minutes, 20 minutes, half an hour to appear and go. So it's a matter of observing the sun at the right time of the day to catch one of these, because they occur randomly. So during January, the numbers of C, M, and X class flares, and you can see now our scale is up to 20. Remember, it was up to about 8 a few months earlier. We're starting to see more M class flares now, which is lovely to see, and a wonderful example of an uptick in solar activity as cycle 25 progresses. A beautiful sun looking in the northern hemisphere now, taken on the 3rd of February in white light. Lots of beautiful sunspots to be observed there, and bigger sunspots and more of them as the solar cycle progresses. Now here's an interesting image. It's called a magnetogram. Because these sunspots are caused by magnetic fields, there is a way of measuring the polarity of these magnetic fields. And here's active region 2940. You can see that the green areas are positive or north, and the yellow areas are negative. So in the northern hemisphere, as the sun rotates in that direction, the negative polarity is following the positive polarity in the northern hemisphere during this cycle. But have a look in the southern hemisphere, it's the reverse. The positive polarity is trailing or is following the negative polarity. And this is a feature of solar dynamics. And every 11 years, this polarity switches. So the previous solar cycle, cycle 24 in the northern hemisphere, it was the negative polarity, which was leading across the sun, and the positive polarity was following. That was in the northern hemisphere, and the positive polarity was following, and the positive polarity was following in the southern hemisphere. So therefore, our solar cycle contains, in a magnetic sense, is 2 11-year cycles added together. So it's a 22-year magnetic cycle and an 11-year sunspot cycle that we see. On the 7th of February 2022, there was this beautiful prominence visible from on the edge of the sun in hydrogen alpha. Here's some details about it. It's measured to be 109,000 kilometers high. So remember, the Earth's diameter is about 14,000 kilometers, and this is 109,000 kilometers high. Was it full? Excuse me. Excuse me. And the very next day, that prominence erupted, gave up its magnetic energy, created this huge prominence on the southeast limb, and an image taken from space from the SOHO probe showed a CME, a coronal mass ejection, being flung out from the sun from the region of where that activity took place. So prominences can lead to coronal mass ejections, flares can lead to coronal mass ejections, and they are a phenomenal amount of energy. I haven't mentioned yet, but 100,000s or even millions of atom bombs going off simultaneously is the energy in an M-class flare. So 7th of March 2022, in white light, a lovely large sunspot group down here, AR2960. Bearing in mind this, and he was starting to see features of a large sunspot, the dark inner region, which is called the umbra, and the lighter outer region, which has structures, is called the penumbra. So even sunspots have different regions associated with them. And here's the same sun taken on the same day in hydrogen alpha, some beautiful prominences around the edge. AR2960 with those beautiful chromospheric structures around it. A bit of activity here around 2962 as well. 4th of April, this month, in white light at the top and hydrogen alpha at the bottom, 2978. As we can see here in hydrogen alpha, it's flaring quite vigorously. These are probably C-class flares, given by the intensity of them, but also look at this, lots of filaments. Remember, these are prominences seen silhouetted against the brighter solar chromosphere in this case, and there's a prominence leaving the surface of the sun. Wow, and within the last week, some huge sunspots have rotated into view on the solar disk. AR 2993 and 2994, and there's 2995 following them. And this is in white light. And solar astronomers get very excited about seeing these large and complex sunspots because that means there will be flaring and perhaps coronal mass ejections taking place from these regions. And let's count up the number of C, M, and X class flares over the last month or so. And you can see there's been an uptick in numbers. We're up to, well, scale is 24 now. Lots more M class flares, as you can see the the red tips to the counts here, and even a few X class flares. The most powerful solar flares that we know of are starting to appear. Clearly, cycle 25 is increasing in intensity month by month. Now that's the current situation. Let's have a look historically over the last two solar cycles. Notice the change in the vertical axis here into the thousands of total number of flares on an annual basis. And here is where we currently are in 2022, only 4 months into the year. And we've already exceeded the total number of C, M, and X class flares that we saw for the entire year last year. So once again, a clear indication that solar activity is on the rise. And wow, wouldn't we love to see a year like 2002, for example, over about 2,600 flares were observed during that year. And who knows? But what's the prediction for this year? Well, there's about 500 flares so far this year. And so we're a third of the way in. So we may expect 1,500, maybe a little bit more, perhaps 1,600 for this year. So there's a lot more excitement ahead for us. Now, questions are, how intense and when will solar cycle 25 come to maximum? Well, the official forecast is that it will be a maximum around about July 2025. All depends on which model is used. But however, this is where cycle 25 currently is. It's way above the forecast line of solar activity based on the sunspot number. So the sun is ahead of schedule. And that's the beautiful thing about the sun, ladies and gentlemen, that there's so much that we don't understand about the solar dynamics that we're learning something new from the sun every day. Okay, so that's the official forecast and actual data. And if you go to the BOM site, that is the Bureau of Meteorology Australia, go to their space weather section, you can get an update on what the BOM believes to be the situation with solar cycle 25. And here's the actual sunspot number data. The magenta crosses are a prediction based on the observed numbers so far. And so the BOM are predicting a maximum to occur about midway through next year. About a year from now, solar maximum is predicted to take place. Now, I'm going to stick my neck out and say it's going to be a double maximum, like cycle 24 was. One maximum, then a little dip, and then a secondary maximum. So I reckon solar max will occur, first one, towards the end of 2023, and the next maximum will occur about a year later, towards the end of 2024, perhaps into 2025. A lot to look forward to, ladies and gentlemen. But here is a feature that people who enjoy observing the nighttime sky will enjoy with solar cycle 25 heading closer to maximum. Displays of the southern lights, the aurora australis. And here's a beautiful image taken by Caroline Tan from Tasmania on April the 9th this year a beautiful display of the southern lights, the aurora australis. And as solar activity rises, we'll be seeing more effects of the sun on the Earth's magnetosphere, or its Earth's magnetic field, and with coronal mass ejections and solar wind, etc. We'll see more displays of the aurora australis as time goes on. And on the same night, a beautiful image taken from southern Victoria, and this is along the Great Ocean Road for those who are aware of the roads along the coast in southern Victoria. A beautiful display of the aurora australis with beams heading up, a little bit of a green band here, red beams, the water, even colours reflected in this rock pool here, and how characteristic to see the small Magellanic Cloud in here and 47 Tucanai in the field of view. It doesn't get any more southern hemisphere than this, ladies and gentlemen. Now, just briefly, just in the last few minutes, we'll just go through the equipment that John used to take these images. So he used the William Optics 81mm refractor with a Herschel wedge. So the Herschel wedge simply reduces the intensity of the light and the heat, getting to the eyepiece to safe levels, and a 540 nanometer filter, a green filter, to enhance contrast. And for hydrogen alpha, he used the Lunt 100mm hydrogen alpha refractor, and these machines work beautifully. And to capture them, a Canon DSLR camera. I will say, ladies and gentlemen, all of these images of John were single images. Here's John's William Optics 81mm scope, and here's the Herschel wedge. So effectively, this is simply a refracting telescope with a Herschel wedge put onto the back end of it. That Herschel wedge can be taken off and the telescope used for nighttime viewing, stars and clusters and what have you. So that's a wonderful way to convert your refracting telescope into a solar telescope for white light viewing. And here's the Lunt 100mm solar telescope. Looks like a refractor, but just in here are the specialized optics that select the hydrogen alpha wavelength. And this big knob here is a pressure tuner, which helps to select the bandwidth of hydrogen alpha that gets through to the eyepiece. And importantly, and not visible here within this diagonal, is a special infrared blocking filter to remove the heat that the Etalon is unable to remove. Simply, it is a factor of light and optics, and for visual observation of the sun. And there we have it, ladies and gentlemen. I'd like to finish off by saying cycle 25 has just started. It is ramping up in activity, and at this stage we do not know how intense cycle 25 will be or when the maximum of cycle 25 will occur, but there is a lot to look forward to for us solar observers out there. So I thank you very, very much for tuning in today, for listening to this talk, and I hope you enjoy your day. Thank you very much.
Thank you for that, Russell. We've got a couple of questions. So the first one is from Murray Forbes. Would you get any benefit by combining the 540 and the hydrogen alpha images taken at nearly the same time into one image?
Well, that's a very, very interesting suggestion. It's something I haven't considered, but give it a go. My feeling is that each image is valuable on its own. By combining them, it would tend to detract a little bit from the final result, but have a go and see how it turns out. But that's a very, very interesting suggestion. Thanks very much, Murray.
So we got another question from Ian, wanting to know, are the examples of double maxima in cycles stronger?
That's a very good question. Not quite sure. Could you just repeat the question, Mark?
Are the examples of double maxima in the cycles stronger than the last ones?
Whether it's a double maximum or a single maximum, my recollection is it doesn't per se affect the intensity. For example, we can have a relatively weak solar maximum with a double peak, like cycle 24 was a relatively weak one, whereas we can have much more intense maxima, as we saw in cycle 23 was a double max as well. So it is. And I should just say that the double maximum is a feature of the north-south hemisphere of the sun. So currently at the moment, cycle 25, we're seeing slightly more sunspots in the southern hemisphere than in the north. And so that is why some solar maxima are double peaked. It's simply because of more sunspots appear for a time in the northern hemisphere, for example, compared with the southern hemisphere. But as far as I know, there's no real correlation between whether it's a double peak solar maximum and intensity. Anyway, thanks for your question.
Got one more question for you from Neville Fraser. Does the sun have a magnetic field of its own?
Absolutely, it does. Absolutely. So, yep, the sun has a north-south magnetic field like the Earth does, radiating from the magnetic poles of the sun. But because the sun is a huge ball of streaming plasma, charged particles, the internal motions of the sun means that the plasma is moving, and that moving plasma creates its own submagnetic field. So, yep, so the sun has two kinds of magnetic field. The bipolar magnetic field, such as similar to what the Earth has, but also magnetic fields associated with the moving plasma within the sun itself. And it's when those magnetic fields break out through the sun's photosphere or the chromosphere that we see sunspots and flares and activity like that. Good question.
Wonderful. Now, I don't think we've got any more questions, Russell. So thank you for your presentation today. It was an excellent presentation. It was very interesting. The viewers have found it interesting as well. Always enthusiastic, and great to have you on board for today's stream.
And pleased to present today. Thank you very much for the opportunity.
No worries. Now, moving on. Our next speakers, Barry Adcock and Stuart Beveridge. Barry is an electrical engineer who is retired and was director of the ASV Lunar and Planetary Section from 1968 to 2008. Not very long at all. Barry studied data collection procedures for solar system objects. He has a keen interest in telescope making and optical design, and is a member of the Great Melbourne Telescope Restoration Team. Stuart is the current director of the ASV Lunar and Planetary Section and a telecommunications technical officer who works for Telstra. Tells me he just turns up and gets paid. He has been a member of the ASV for 32 years with an interest in telescope making and lunar and planetary imaging. Their talk will cover 50 years of observations of the Great Red Spot with the centenary year of the Astronomical Society of Victoria and the Lunar and Planetary Section that the Lunar and Planetary Section has conducted, collected and processed over of the body of the solar system for over 50 years. The Great Red Spot of Jupiter is well known to a wide section of the community, and the slow decrease in size of the spot has created concentration of public interest. Barry and Stuart, the floor is yours. We look forward to your presentation.
Good morning, everyone. This is the 25th National Australian Conference that I have attended. I have to point out that my aim is to attend 50, but that may be a little bit optimistic. The Lunar and Planetary Section of the Astronomical Society of Victoria was formed in 1962 and has been functioning as an observing group ever since. And as Mark pointed out, I took over the section director in 1968. And during that time, we have collected and analysed a huge number of drawings and central meridian timings and photographs in the analysis of planet Jupiter. As it's the ASV's 100th anniversary, we thought it would be appropriate to perhaps look back at the way we used to do things 50 years ago, in fact 60 years ago in my case. And in 1958, I had just finished making a 5-inch Newtonian telescope, and I borrowed that camera from my sister and I took that picture of Jupiter. It's not a very good start, of course, because the great red spot is not obvious on there, and we can't make much of it. But just as a reminder, a very quick reminder of the situation, the great red spot is located in the south equatorial zone, the south tropical zone of Jupiter. It's nestled into the southern edge of south equatorial belt, and due to chaos in that area, particularly in recent times, it's a bit hard to explain exactly where it is. But going through the nomenclature of the planet, I've put a disk of the Jupiter there with the north at the top, south at the bottom, and the belts are labelled away from the equator, the south equatorial belt, etc. And on the other side, I've labelled the zones, and the equatorial band, of course, is the middle section. And on an actual photograph, these things line up fairly well. Jupiter is not a solid body. It has 3 distinct rotation periods. The first one is the equatorial zone, known as System 1, about 9 hours 50 minutes. The second is System 2, which applies to the rest of the planet, north and south of the equatorial zone, 9 hours 55 minutes. And a third rotation period, the 9 hours 55 minutes 29 seconds, which is considered to be a radio rotation period. There are local zones, of course, and along the edge of the belts there are currents of atmospheric disturbances that have a much different velocity, and these currents, of course, are what generates the cyclones and the anticyclones along the edges of the belts that we're about to study. The local currents in that picture just show that the great red spot is, in that case, is drifting in a westerly direction at 11 kilometres per hour. I want to talk about the great red spot in 3 aspects. First of all, I want to talk about its position in longitude, and then we want to have a look at its its size, and then after that we'll have a look at its shape. And in past times, the rotation period of the planet is basically associated with System 2 because it lies in that area of the planet. It's an irregular rotation period, and it's therefore it seems to drift in longitude with respect to System 2. And out of the times we've been able to draw that graph, starting at 1965 at the bottom and going up to 2005, the longitude of the great red spot with respect to System 2 rotation has varied quite considerably. And the question is, how do we know this? And in the past days, there were 2 methods of working out the longitude of the great red spot. The first is through central meridian transit timings, and the second was through measurement of photographic prints. And we'll just have a look at that those procedures briefly. The central meridian transit timing, Jupiter may appear in that configuration in the eyepiece, and the best way to perform a transit timing is to orientate yourself so that the bands are horizontal. That's just a procedure which works well. The central meridian itself is a straight line that joins the north and south poles, and that line is in fact called the central meridian. And the idea is at the eyepiece to time the passage of an object, in this case the Great Red Spot, across the central meridian. And in those days it was considered that it was possible to do that timing in plus or minus less than 2 minutes accuracy. And in doing that, we were able to convert that time into a central meridian of the planet Jupiter. Now, the central meridian at any particular time and day are listed in astronomical ephemerides. In that particular case, that's the ASV yearbook, and we use that to convert the time into a central meridian. Now, for the sake of time, I'm not going to go through this in great detail. You could replay it if you wish to have a look at it, but for this particular time, I picked the 26th of February 2015, and on the page of the yearbook associated with System 2, I've converted that time into a longitude, and that came out to 222.7 degrees. Just moving, just moving on. Having the central meridian of the Great Red Spot, we're able to draw strip charts, and that's an example of a page out of our yearbook in 1976, and it shows the way the Great Red Spot appeared during that year, and it's plotted as a function of longitude along the horizontal axis. And that was the rest of that article. If anyone wishes to look it up, the ASV journal, it's in April 1976. During that time, we took many photographs of the planet, hundreds in fact, and I'll come to that point later. But the full disk drawings displayed the best way of working out where the Great Red Spot actually was. And on the right of that slide, we made notes of the central meridian of various objects. That's another strip chart that we made in 1982. Shows the Great Red Spot at a orientation of about 50 degrees, and also the white ovals that appeared in the south temperate belt drifting towards it. And yet another strip chart of the Great Red Spot in 1983, and at the bottom there I've noted that the Great Red Spot has moved from 55 degrees to 35 degrees in 30 months, and it's moving at at a rate of about plus 14 seconds with respect to System 2. In those days, I used to send all of the original observations into the Association of Lunar and Planetary Observers in America, and I used to take photocopies of what we had done. And that's a photocopy in those days, and it shows how poor photocopying machines were in the 1980s, because that's a pretty ordinary slide. But anyway, the Great Red Spot on that particular slide was timed. The center was timed at 19 hours, 13 minutes UT. And on our graph that I showed previously, that would be one of the points on that particular graph. Measurement of photographs was not easy. In those days, I made a camera out of balsa wood, and it had various backings. There was a backing for a 120 size film or 35mm film. I had a shutter that I bought from a scrap camera place, and it was a bit like a single lens reflex camera, but you had to raise the prism, which I used for aligning. You had to raise that manually, and we were able to take pictures of Jupiter. But The problem from a measurement point of view is that we never ever knew where the edge of the planet was. The problem was that Jupiter exhibits a very, very serious limb darkening. The moon does as well, and also the sun. If you take a picture of the sun, the limb is much darker than the center part of the planet, of the sun. But on Jupiter, it's very pronounced, and I tried all sorts of dodging techniques to try and work out exactly where the edge was. So without knowing just how big the planet was on that photographic print, it's very difficult to actually make a serious measurement of exactly how big or where the spot actually is. So we proceeded on from that. To measure the central meridian or the transit timing of the center of the spot is reasonably easy, but to measure the transit timing of the edge is not so easy, and that gets tangled up in optical illusions that you see in kids' books, where you ask which side is bigger or where the center of the pattern lies, and the great red spot being unsymmetrically placed means that the timing is much more difficult. In recent times, we've shown that that's the graph really from central meridian transit timings that we made up until about the year 2000. In recent times, the red spot has accelerated greatly towards the western limb, and even now in the year 2022, it is now past 360 degrees. So that's the way the spot has accelerated in recent times. In that time, the gradient at that end of the scale was 4.4 degrees per year, and now it's running at about 17 degrees per year in a westerly direction. The size of the Great Red Spot now is, people interested in astronomy will know that the Great Red Spot has been shrinking, and there's even doubts whether it will survive. In 1881, that drawing was made of a spot that shows an enormous elongation. In 1879, Common took the first picture of the Jupiter, and again, the elongation is very pronounced, and I've estimated those to be 35 degrees and 34 degrees. In 1971, I took the picture that I showed earlier, again showing the Great Red Spot large and elongated. The fact that it looks black in the two photographs was that in using films in those times, even though they were supposed to be panchromatic films, they were in fact blue sensitive. So anything that is red will come out as black on the print. And in 1971, I estimated that the size of the spot was 25 degrees. The shape of the Great Red Spot changes as it's been shrinking, and to work out the shape of the spot, we need to have a look at. We need to observe it from the latitude that it is in, and to work out the latitude of a spot, you can look up references in Peake's book, The Planet Jupiter, or John Rogers' book, The Giant Planet Jupiter, which describe how to achieve the calculation of the longitude of the latitude of the spot. But there's a diagram of Jupiter. There's the equator. There's the Great Red Spot at a certain latitude D, and we look at Jupiter from a point known as the sub-Earth latitude. The sub-Earth coordinates are given in ephemerides, such as the Astronomical Almanac, and they basically, if you go to Jupiter and stand at the sub-Earth coordinates, of course, Jupiter is a gaseous body and there's nowhere to put your feet, but if we could stand there, the Earth would be directly overhead at Jupiter's zenith. So we need to know that value to work out the actual angle of the great red spot on any particular print. And we wish to observe the spot by looking at it in that direction so that we can see its true shape. Hence we need to know D and also delta, the sub-Earth point. Well, the estimate in 1971, and again, I'll point out I didn't know where the limb of Jupiter was due to limb darkening, but we can go through an estimate, and we find that the south, just by looking at the print itself, it looked like the South Pole was pointing towards us because the south equatorial belt has quite an arc to it in a northerly direction. So I actually measured the shape of the great red spot with a ruler on this screen, and I found that in longitude it was 21 degrees, and its apparent width in latitude was 11 degrees. And I worked out from that the latitude of the spot itself on Jupiter was about 22 degrees, and the width adjusted for that longitude or latitude was 11.2 degrees, and the spot came out to give that shape in 1971. Now, just looking at it in recent times, that's a picture taken in November of 2021 by Stuart Beveridge. And again, going through the same measurements, we came up with a estimated spot size of 8.7 millimeters, and in comparison, the spot has shrunk to that size from 1971, but it is very much rounder. And in fact, it's in latitude, it hasn't really shrunk much at all. And it's an interesting study to continue as to why the spot may be confined by the south equatorial belt and the south temperate belt, and its north-south width is not altered very much at all. So hopefully that gives everyone a picture of the way things occurred in the pre-digital day. And now I'll hand over to Stuart for a description of more modern tackle of the problems.
Okay.
I can stop sharing, I presume.
So Mark's put mine up. So, I'd just like to continue on this talk. Thanks, Barry, for part one, and talk about the new age of planetary imaging using digital cameras. So, the Philips 2Cam Pro was a webcam featuring a CCD sensor, giving an effective resolution of 640 by 480 pixels. It revolutionized planetary imaging in the early 2000s. You needed to attach an adapter to fix it to your focuser though, because it was a webcam designed to hang off your computer screen. You could either make one up yourself or buy one off the shelf. And to make one, you could use a 35mm film canister, which just happened to be, they just happened to fit very snugly into a 1 1/4 inch focuser. So you can see here that the imagery is already starting to improve dramatically here, where on the left, you've got the raw image taken by the 2Cam, and on the right is the processed image from the 2Cam of Saturn. Software such as Registax came along, which was used for frame stacking and wavelet sharpening, producing images of the planets that were previously not possible by amateurs. Most importantly, for studying Jupiter, another software package was developed known WinJupos, which I'm about to cover now. So on the 1st of May 2003, the first alpha version of WinJupos arrived on the scene. It had the ephemeris module and the measurements module. The ephemerides and measurements module is what interests us, as it allows us to make direct measurements of the GRS as well as other features of interest. So I'll start with method 1, which uses the central meridian line to measure the CM2 value for the leading edge and trailing edge of the GRS as it moves across that meridian line in a westerly direction as previously described by Barry. It is then measured in the field within the red box below. So it's basically the same as what Barry was doing, but all put into a software package and made a lot more convenient. So you'll need to wait about 12 minutes or so for the other end of the spot to cross the central meridian. And you can see in the figure below that it is has traveled west. When this happens, record the time and put this into the WinJupos to get a CM value for the other edge. And you can put dates and times in the top left corner in the WinJupos package, as can be seen inside the green box. We now get the length of the spot in CM2 longitude by subtracting the two values. So in this example, it was 313.8 degrees minus 296.2, which equals 17.6 degrees. Finally, multiply this length by 1187, which is a figure I got out of the British Astronomical Association's website, to convert CM2 longitude into kilometres. The length of this example, which was the 6th of April 2019, was measured at 20,891.2 kilometres. The next method is similar to Barry's description of the measuring prints, or the equivalent of it, and it uses the WinJupos measurement module. And this is the simplest way of doing it, where you simply go to the miscellaneous heading as shown here in the red box. And then just under that, you've got another box called measurement distance. As soon as you click on that, it gives you some crosshairs, and then you can just simply go down to the great red spot and click on either side of it. Then move the crosshairs to the end of the GRS and click again. This leaves the red line drawn as per below. I think you can just see a sort of a pinky red line there. Then you simply just read off the distance under the measure distance box. In this case, for my image below, from the 5th of October 2021, the measurement was 15,768 kilometres. Barry Adcock earlier mentioned limb darkening as a big problem on Jupiter. WinJupos has solved this problem in the measurement module in the following way. The image on the left shows Jupiter from my data on 23rd of September 2021. Note that the edge on that image on the left is difficult to see. However, using a WinJupos function called LD compensation, which stands for limb darkening, the image in the center shows how the edge of Jupiter is now clearly defined, albeit looking fairly terrible. We don't mind at this stage because all we're after is sharpening that edge. The image on the right shows the result of hitting the F11 button, which is a WinJupos function, and using the arrow keys to clearly fit the frame around the edge, and then turning LD compensation back off. The other important consideration is to use WinJupos file naming conventions in your video capturing software, such as Fire Capture, to automatically fill in the date and time accurately in WinJupos. Once this has been done, then the measurements can be considered accurate. But there is one last thing you need to do in WinJupos, and that is to record the observation, the latitude and longitude of where you observe the planet from. So getting back to the Great Red Spot, in 1979 we got an image from Voyager 1, which was the beginning of getting some very impressive images of the Great Red Spot, and it was recorded on this occasion as being 25,210 kilometres. The next evolution of getting sharp images was in the 90s, when the Hubble Space Telescope came on the scene. And we can see here on the right, we've got comparisons from Hubble of 1995, where it was 22,060 kilometres. This is the width, not the height that we're talking about, of course. In 2009, it was just under 18,000. And in 2014, it had shrunk to 16,000 kilometres. Then in 2001, on its way to Saturn, Cassini spacecraft photographed Jupiter as seen below, and calculating the GRS at 18,500. Then in 2015, Cliff Ashcraft, who was an ASV member and lives in New Jersey, imaged the GRS and calculated it to be 16,200. So according to astrophysicist Mike Wong of the University of California, Berkeley, over the past year, GRS winds have been picking up, as previously described by Barry in his presentation. According to new research published in the Journal of Geophysical Research, and the spot is changing shape. It is becoming less cigar-shaped and more circular. Then in 2019, a network of amateur astronomers around the world captured fragments of the GRS flaking off. And as an example of that, amateur astronomer Dr. Andy Caselli's images below were taken from Sydney from his backyard. So you can see now that in 2019, amateur images have become very impressive using modern CMOS cameras, large telescopes, and more modern software. But in research published in the Journal of Geophysical Letters later that year, scientists said the event was not a sign the spot was falling apart. Instead, it was caused by a series of smaller storms drifting across the top of the red spot. The surface events on the spot weren't really threatening to break apart the red spot because it was much bigger and deeper and more organised than that, said Dr. Caselli, who was recognised in the paper. And he concludes, it's just amazing to collaborate with professionals, to be a relative average person in a backyard and be able to do some real science. Also backing that up, data from Juno confirms that the GRS was not breaking apart. And from their report, from one of the Juno team's reports, Jupiter's Great Red Spot has had a hard time in recent years. It has been steadily shrinking in the east-west direction for decades, and recent encounters with smaller vortices has led to enormous flakes of reddish material being drawn out of the spot itself. These flaking events, though troublesome for fans of the best-known storm in the solar system, do appear to be superficial, only affecting the reddish hazes that sit atop the vortex. And you can see here in this image that it looks like material of the GRS is being drawn out. So just going back to one of Barry's images, and this is the oldest known photograph of Jupiter by Andrew Common. He was an English sanitary engineer and amateur astronomer. He took the first Jupiter photograph in 1879 using his homemade 36-inch f5.8 reflector using the brand new Eastman Kodak dry silver bromide plate with a 1 second exposure. And so we can see here that the distance from pole to pole is 133.7 thousand kilometers, but the distance across the equator is 142.98 thousand kilometers. What this means is that Jupiter is an elliptical looking planet rather than a circular planet. And the yellow line there represents the Great Red Spot latitude circle. And so from there, we can bring down those green lines and make an approximated measurement of Common's image as 45,900 kilometers. So just to summarize all these measurements, the first measurement here is from Common, showing a width of just above 45,000 kilometers back in 1879. The second image on this chart shows the GRS from Voyager 1 and Voyager 2 in the late 70s, early 80s. Then beyond that was the Hubble Space Telescope images, going up to the mid to late 90s, followed by the Cassini flyby in 2001. And this says my images, but this was put together once again by Cliff Ashcraft, and his images and mine and Barry Adcock's and others are all in agreement on the size of the GRS. So using this as a trend line, Cliff has calculated through this equation that if this trend line continues, the GRS will be gone by 2077. So what this means is that as amateurs, we should continue to image Jupiter as often as possible, especially of the Great Red Spot, and take measurements and see if this trend line is going to continue, or it may even change in the next few years. Nobody really knows. And this just concluding, that's another image of mine from 21st of October 2021 through a 12-inch f5 Newtonian, showing that the red spot here is a lot more circular than what it has been in the past. So that's the conclusion of my talk. Back to you, Mark, for any questions.
Well, you answered the question, one of the questions, well, the only question that's in the chat at the moment. You answered it. When or will the red spot one day fade away? And it sounds like it will in 55 years.
Yeah, unfortunately, I'm probably not going to be around to see that. So, but what we can do in the next 5 to 10 years and continuing on is just see whether the trend is going to continue or change.
It'll be an interesting process over the next the next 5 to 10 years to see what happens.
I think these predictions assume that the present weather conditions will continue in a linear manner, but all sorts of things can happen to turn that around. And I think the prediction of what will happen in 50 years' time is not on very strong grounds.
Well, we can't even get the weather prediction right one day out, so. Here we go. We have a question for the two of you. To image the Great Red Spot, what number of frames is best?
Oh, I think Stuart and I do much the same thing at the telescope with a digital camera. I take an exposure of Jupiter using an AVI configuration for 2 minutes, and that produces about 15,000 images of the planet, which we then use to stack and to process. But if you expose Jupiter much longer than that, its rotation it becomes a nuisance, and both of us have zeroed in on an AVI of about 2 minutes long.
And Barry
There are
uses
other people are doing different things, and there's probably no right way or wrong way. It's just what you get used to, and try to do the best you can.
That's exactly right. We both, Barry and myself, both use around 100 to 200 frames per second, and an exposure of around 4 to 6 milliseconds to try and freeze the atmosphere. Just in addition to that, whenever we go out to image Jupiter, and quite often Barry will message me to say this is going to be a great red spot night, you can determine this a number of ways. You can look at the ephemera section of WinJupos for an accurate prediction of when the GRS is going to be out. Or from my phone, which is an Android, there's an app called Jove Moons Pro. And in Jove Moons Pro, it's very easy to use. You look it up, and it tells you what Jupiter is looking at right now. And you can say, when is the next great red spot transit? And you just click on it, and it tells you the time in Eastern Standard Time. So it's easy to predict whether it's going to be a GRS night or not.
Now, we have another question for you. Have you looked at any images of Jupiter taken in Australia from the late 1800s?
Well, I haven't done that. I'm not sure that. I don't know that there was a lot of work being done. I know some pictures were taken through the Great Melbourne Telescope of Jupiter and Mars in the late 1800s, but I haven't analysed them, unfortunately.
I think that's all the questions we've got. Well, we've had. So thank you, Barry and Stuart, for joining us and giving us a presentation on Jupiter. As Ballarat Observatory says, dedicated application of observation of over 50 years, and to those following and carrying on the work. It is 50 years of imaging one planet is amazing dedication, Barry, and to see the progression through the years, the quality of the images increase was wonderful. Thank you to. Oh, hang on, we do have one last question. John wants to know, what is the reference point to know that the Great Red Spot is rotating relative to the rest of Jupiter?
I think many. I can't quote the exact date, but this starting point of System 1, 2, and 3 was determined by the Astronomical Union, and it has become a reference to the rotation rates which are used ever since. And it's the ephemerides that I showed either in the yearbooks or the Astronomical Almanac that calculate where the longitude of the central meridian will be on every date of the year. And that's all calculated from some datum point many years ago. And it's fair to say, I guess, that of the 3 rotation periods, there's almost nothing on Jupiter that rotates at those speeds. But it does represent a reference framework on which to judge the rotation of everything on the planet.
Thank you for the answer. Hopefully that gives John the answer that he's looking for. And as I mentioned, thank you for joining us for today's first stream. Our next stream kicks off at 11 a.m. and covers topics related to the 1922 total solar eclipse and the 5 total solar eclipses coming to Australia. Remember that there are still tickets to the ASV's Easter NACAA raffle. It'll be drawn at 5:30 today at the end of the 4th stream. So head to asv.org.au to grab your tickets before it closes. The link is available on the website. $5 a ticket with all funds going to our remote observatory project. We certainly hope you've enjoyed the stream this morning because we've enjoyed bringing it to you, and we look forward to seeing you at 11 a.m.